Hi guys, this video is going to continue with lesson 2 on the kinematic equations. And we did a lot of this in class, but I want to just pay attention to a few things down here. Now, some of them are self-explanatory, but I want to go through as many of them that we need to. Basically, one thing is, these are the 3 kinematic equations we're going to use. And so those are really what you need to focus on. You do not need to memorize them. But you do need to know what they are and how they work. So for instance, I'm going to go through right now and talk about the variables. The V stands for velocity. They don't have a subscript on it, but I want to come back to that in just a minute. V sub O is the initial velocity. A is acceleration and T is time. Now I want to go back to that V. There is no subscript on it, but I oftentimes will call it V sub F so that I remember that's the final velocity. Because sometimes you get in the midst of these problems and you can't remember what's what. So sometimes it's just a lot easier to call that V sub F. Same thing down here. You would call that V sub F for final velocity. That's all of them in the top equation. Okay, in this next equation we have an X, which is it stands for your position, but again, even though there's no F on it, I would call it the final position. And X sub O, I would say that that is the initial position. And then with that is a delta X. And I think we all know that delta X is the final minus the initial. There are some times when they don't have a delta, but maybe it's easier to talk about the delta. So we'll, I think, run across those as we discuss those as we run across them. Another thing about these equations is if you look at them, there are a lot of variables. And so our steps here, a lot of you know in your head in a math class how you're supposed to solve the problem. You're supposed to list out your variables and do all this, but a lot of us don't do that because those problems are so easy for us that we just don't do that. I think it's going to be helpful as you're starting out in physics to go back to that. So things like drawing a diagram, do that so that you can make sense of what's going on. Listing all the known and unknown variables. This is really important, because these problems will have a lot of variables and you will really have a hard time figuring out where to go unless you list them out in an organized way. And then number 3 goes with that. Pick an appropriate equation, because if you don't know what variables you have, you're not going to know what equation to use. So for instance, if you look at these 3 equations, once again, a lot of variables going on. But this top one, do you notice that there is not an X in here? So we're going to use that when we don't have an X or we don't need an X. So this one doesn't need distance. So anytime you have a problem that doesn't ask about distance, doesn't include distance, you will use this top equation. Now the middle one includes everything. So that's when if you know a lot of stuff and you're trying to find something, whatever, this middle one has just about everything in it. But the bottom equation, you might notice, it is missing the time variable. And so if you don't have time or you don't need the time, then this is the equation to do. Now you wouldn't know that unless you had listed out what you do have. So that's an important thing. Simplifying the equation. Things like, can you look at this middle equation for just a second? Can you see that maybe I could subtract that X sub O to the other side? And if I subtracted that X sub O to the other side, then I could rewrite this as delta X is equal to VOT plus 1/2 AT squared. So sometimes it's helpful to kind of rearrange the equation into the order that we need it, or using the variables that we need, or what have you. And then we're going to plug our variables into the equation, solve the equation. Now, significant figures. I believe we've talked about this a little bit in class, but sig figs are not nearly as important in physics as they were in chemistry. It was a big deal in chemistry. In this class, we basically are going to stay to around 2 to 4 significant digits. You don't have to get any more picky than that. That's fine. The last one, though, is also important. Question the answer. In other words, is it in the right units? Does it make sense? Is it logical? Is it positive and it's supposed to be positive? Or is it negative and it's supposed to be negative? All those things. Think about your answer when you get it and make sure the answer does make sense. All right, because these are on video notes, if you have questions that I have not addressed just now, what I want you to do is go over to the margin and write your questions down here. Now, maybe you don't have any questions, that's fine. But if you do, that's what this margin is for. Write down the questions that you want to ask me here. Okay, if there are no questions, let's turn the page. All right, here, this first example is a pretty basic example, but it gives a good example of, look at all the variables that are involved. We have 0 to 27 meters per second, that's 60 meters per hour, 60 miles per hour. We have 10.9 seconds, and then the question is asking about maximum acceleration. Let's go through and define our variables here. So we're going to use v for velocity, we will use t for time, and a for acceleration. Take a second right now to fill in what you would do for each of those. You should have filled in initial velocity is 0 meters per second, final velocity is 27 meters per second, time is 10.9 seconds, and we are looking for acceleration. If you go back to the other page and look at the equations, so I'm talking about these equations. If you look at these equations, can you pick which equation you should use? All right, as you look at that list of equations, you should have chosen this equation. Final velocity is initial velocity plus a times t. So now that we have an equation, now we're ready to start plugging in some numbers. So we have 27 meters per second. As I plug in these numbers, I'm going to also put my labels on there because that's going to help me make sure that my answer in the end is in the right units. Okay, my final velocity is 27 meters per second. My initial velocity is 0 meters per second. And then A, that's what I'm looking for. And time is 10.9 seconds. Okay, so because this is 0, I think we all understand we don't need that. That's 0, it's gone, so that's nothing. To solve this now, we need to divide by 10.9 seconds. Okay, so when we do that, when we divide by 10.9 seconds, let me tell you a couple things. Back to the units for a second. We want to make sure we're keeping track of our units. Seconds here divided by seconds here. Okay, it's meters per second divided by seconds. That means this unit on the left-hand side is going to be meters per second squared. And then I need to go to my calculator and divide this out on my calculator. And when I do that, I get something like 2.48 or 9. And I'm going to go ahead and round that to 2.5 because that would be the significant digits. And so I get that is equal to A. In other words, my acceleration is 2.5 meters per second squared. Let me talk about that answer for just a second. The units, meters per second squared, that does match with acceleration, so at least that part's right. We need to think about positive or negative. Should this be a negative acceleration or should it be a positive acceleration? Well, we're going from 0 to 27, so it does need to be positive, so that's right. And then as far as 2.5, is that a reasonable answer or not? We don't really know because we don't really fully understand some of these yet, but 10.9 seconds, 2.5 meters per second, it gets up to 27. That seems like it is making sense. So that is the final answer, is 2.5 meters per second squared. Once again, if you have questions, if there's anything in here you didn't understand, write your questions out in the margin so tomorrow when you come to class you can ask me those questions. Let's look at the next example. Some fool is texting while they are driving at 30 meters per second and fails to see a stop sign until it's 10 meters away. Assuming they make a full stop in the correct location, what is their acceleration? Well, first of all, they're going super fast. If 27 meters per second is 60 miles per hour, this guy's going over 60 miles per hour. And they have to stop in 10 meters. That is a really, really short stop. Realistically, not sure if they're going to make that, but let's see if they do, what kind of acceleration are they experiencing? All right, so once again, we're going to pause here and write down your variables. So pause the video, write down what you think the variables are going to be. Okay, you should have come up with the initial velocity is 30 meters per second. The final velocity is 0 meters per second. I called it delta x. If you wanted to have a final distance and initial distance, you could. I just called that delta x. And then the question is, what is the acceleration? So once again, we're going to look at those three equations. We're going to decide which one to use. And so when I say three equations, these are the equations we're talking about. Decide which one of those equations we need to use for this situation. Hopefully, you chose this equation. Final velocity squared is equal to initial velocity squared plus 2a delta x. And so now we can start to plug in the information that we know. We know the final velocity is 0. And I do like to put units, but since it's just 0, I don't think we need to put our units on 0. Then 30 meters per second, and I'm going to put this in parentheses before I square it because the units are also going to get squared. Okay, A is what we are looking for, and delta x is 10 meters. Okay, so now I'm going to go through and simplify this a little bit. I still have 0 on the left. On the right, I have 900, and I'm going to call this meters squared per second squared, because when I square that, I'm going to get meters squared per second squared. And then with this, I have a 2 times 10, that's a 20 meters, and I'm multiplying that times A. A is also what I'm looking for, so I need to do a couple things. One thing is I need to move one of these to the other side. It doesn't really matter which one. I'm going to subtract my 900. Okay, so I'm going to subtract my 900, and that's kind of messy, but that says negative 900 meters squared per second squared is equal to 20 meters times A. I need to solve for A. I'm going to write over this. Hopefully you can see it, and hopefully you have some space on your paper. If you need to come up here to this space, you can. But I'm going to divide by 20m, and on this side by 20m, where m is meters. So when I divide that, I get a negative 45. Let's talk about the units. This meter is going to cancel with one of those meters, so I'm left with meters per second squared. On this one, the 20 meters and 20 meters cancel out, so that is my acceleration. Let's make sure that answer makes sense. First of all, it's negative. Is that appropriate? Yes, they're slowing down, so negative acceleration is appropriate here. Secondly, it's a huge number. You might not realize what big of a number that is, but gravity is about negative 10, so this is about 4 times gravity. In other words, they are experiencing 4 Gs. Is that an appropriate level? Well, remember when we started, we said this guy's going 60 miles per hour, so this one's going more than 60 miles per hour, and they have 10 meters to stop. Do you know how far 10 meters is? Well, do you know how far 10 yards is on a football field? Okay, are they going to go from 60 to 0 in 10 meters? If so, they're going to experience 4 Gs. So yes, this is an appropriate and realistic answer. Now, assuming they make a full stop, I doubt it. They probably did not make that stop, but if they did, this is the acceleration they would have to experience. Okay, those are the first 2 examples. I'm going to stop the video here and make a second video for examples numbers 3 and 4.